Let's just everyone for joining us. We've got a really good turnout here today, and no doubt got a really good speaker as well. So thanks Dan for coming down. Just a quick one from me. Most of you that have already attended before already know the script, but I'd just like to let everyone know that this meetup group has got a couple of sponsors. The first one is JetBrains, and they kindly give us a license once a month to raffle. So if you've seen the QR codes around there and you've scanned them, you'll be in for a chance to win a license at the end of our meetup. We're going to be giving that away later on. There's a lot of things you can do there, like .NET Trace and Rider and that sort of thing. So if you don't get one this time, come down next time, and I'm sure you'll have a chance to win. But yeah, usually they're quite expensive, but for us, you get with the license, you get 12 months free. So thank you, JetBrains. And that's there. If you scan the QR codes, you'll come to our landing page. The first one is for being put into the chance to win the JetBrain license. It'll just take your email address and name. And the second one is just a little survey for Barclays Eagle Labs who kindly give us this venue. So what this venue is it's a sort of hot desking lab, so you can book meeting rooms here. So if you was ever in the market for some remote working or getting a group of you together, but you wanted to use spaces like this to host your own meetup groups, do check them out. They're really nice, and we've got all the facilities here to help you go through that. And then one of our sponsors as well, who's sponsored this today, is Summit to Tech. We're really picky with our sponsors because we don't want to sort of like you all to come in. We're developers ourselves, we're not recruiters, and we want to give you the very best and the free content. Hence the reason why we're live streaming today on our YouTube channel for the very first time. So that's exciting. So I hope that goes well. And thanks to Chris and Samson, the volunteers here as well today. But Summit to Tech, they do something really special. So they help junior developers. It's something that's works closely well with what I want to do, is help juniors get into the workplace. And what does that mean for you? So if you are a senior developer, if you're managing a team at the moment and you've not got the time to spend and dedicate a lot of your time with juniors, this is where Summit to Tech will really shine. They will help put a program together to build up developers to a certain level that the company needs. It is, for me, I'm currently going through one at the moment, and it's completely free. Don't ask me how, but there are tax reasons that the company can use, like you come to the levy, so it's actually just a really good incentive to go and see what they've got, have a chat, and yeah, like I said, I won't be putting this out if I didn't think anyone would benefit, so I really do. We really appreciate you, you're in the market, go check them out. That's all from me. I'm going to pass you over to Dan, and then I hope you all enjoy your evening.
Right, I'm going to see if I need the microphone. There's a suspicion I might not. Hi, my name's Dan Roberts. I work at Stack Overflow. I'm tech lead of the team that's working on improving our search. I'm going to be talking today specifically about tech search. In a previous life, I worked at a tourism web company where we did loads of search to do like metadata filtering, so pre-entered values or limited values. Like, I want to stay in Liverpool city centre on 3rd of September, 3 nights, 1 room, 2 people, hot tub, dog friendly, that's in combo, and pre-selected, so, limited options. Now you can combine metadata searching or metadata filtering with text search, but it's not where my attention is lately. It's not what we're talking about today. Now you might be wondering what search a Stack Overflow, because let's face it, most of the public traffic comes via Google. I tried to find an authoritative source to back up this most public traffic claim, and I failed. So I tried something called Complexity.ai. I don't know if you all know this. Complexity.ai is a free search engine that uses generative AI, very cool term last year, to answer natural language questions. Now the irony is not lost to me that I'm supposed to be an expert on search, and I couldn't find what I wanted with Google. It's a hugely powerful, amazing search engine. It's also not lost to me the irony that there's a lot of people tell you generative AI, it's going to be the death of Stack Overflow, and that it's going to happen in the near future. I don't believe in that yet. What I'm going to do is use this as an example to illustrate search is hard. Now something important to note is that I've been referring to like our public data in Stack Overflow. It's a public site, we all know, we've all been on, everything's And what we do, we have another product called Stack Overflow Teams. And it's like a private version of Stack Overflow. Which one company has, they pay us to have it. They populate it with data. I've worked at least one company that had their own teams. This is like a fictional product that nobody actually wants. And I know people in a bit of various other companies that have their own teams instance. I don't know if they like us to advertise their names, so I'm not going to mention any, but if you saw the list of people that have it, you would recognise a lot of these companies. Now, because it's private data, it can't be indexed by Google. You can't search it through Google, you can't search it through Perplexity. So the users of Teams having an effective search is crucial to share information, to avoid duplicating information, to find what you need and for it to be effective. Basically the same things that we need through the public site, we need the private site. We can't rely on other people to solve this problem. Now, before I get into all this recent developments about search, I'm going to have a little recap, run through on what did search used to do. Lexical search is like an intuitive way to implement search. Someone said, as a developer, work out, design text search. You essentially get your documents, big pieces of text, and you break them into individual words. And then when you do a search, you break a query into individual words and try to match all the words to documents. Lexical means related to words in vocabulary, so it's descriptive, it makes sense, that's what it's called that. Now I know personally that it feels like an intuitive way to implement search. Some years ago, I decided I would write my own full text index. I was having a fight with Lucine at work and thought, how hard can it be? According to the GitHub commit, it was 13 years ago that I started this, so that's bad. But it's a fun project. It's a fun project because you can get something useful, working quickly, and then iteratively layer complexities, edge cases, all the interesting handling of things that you might not initially think of in the first place. You can build it up. So the first thing that we need to be able to do, oh yeah, I forgot, I use my search, my indexer, to do a search on my blog. So if we were going to do this, build a lexical index, the first thing we need to do is break down documents. This is called tokenization, and this is context. A token is a word. So tokenization is splitting a big document into words. Once we're able to do this, we've got the building block to actually index content. Because here, indexing content means making the text documents that you want to search over. So we break each of them into individual words, generate a lookup tree or a dictionary, such that if you have a specific word to search for, you can get a list of all documents that that word appears in, and how many times it appears in the word. And then we work out how interesting a particular word is. If someone had a query, cats and dogs, 3 words, then we want to find documents that have all of those 3 words in. Cool. But we also want to return this list of documents such that the most relevant ones appear at the top. Now, if a 10,000 word document has all those 3 words in, but only has cats in once, it's probably not the most amazing choice. Whereas if there's a document which has all 3 words but has cats and dogs all the time, it's just talking about cats and dogs, cats and dogs, cats and dogs, cats and dogs, that's probably going to be much better than actually one that higher up in the list. One way to calculate this interestingness is something called IDF. Term frequency, document frequency. It's a way to calculate a weight for a unique word within a document by looking at how often that word appears within a single document, that's called term frequency. How often is that word in one document, compared to how often it appears across all documents, that's document frequency. So in the cats and dogs example, if the documents that we're indexing are English language content, the word and is probably going to appear often in any single document, so that would give it good term frequency. But also, it probably appears in nearly every document. So that means the inverse document frequency is going to quash that score. The point is, the idea is that you want to be able to differentiate one document from another. And if everyone has the word and is not a good way to differentiate one document from another. Now let's say the documents that we're indexing are all of the English language Wikipedia pages. The word cats not being super common across all these docs. So the inverse document frequency is going to be like, yes, interesting, exciting word. And documents which have the word cats in many times are going to have a high score. Now on the other hand, if the the documents we're indexing were English language, but they were from like a vet, surgery's newsfeed, probably the word cats appears more often across a larger proportion of the documents, and so it's not going to receive as great a weighting due to this inverse document frequency that it would if we were talking about documents that aren't just about animals all day. Still receive it as a more interesting word, but it's not going to be as interesting as if it was like in the corpus, which just means all the documents of all of English and Wikipedia content. So, okay, cool. Now we finally fully understand kind of how you index documents. And with this cats and dogs example, we kind of also know how to query the index. And just to summarise it again, if someone runs a query, take query text, cats and dogs, split it into individual words, cats and animals and dogs. And then we use this lookup tree to quickly find all of the documents that have all these words, and then we order the results to give the best matches first, based on that scoring, about how rare or common each word is, and how often it is. Easy. Well, not very that easy, otherwise people would have been more solved from. And let's find out why it's not easy. So as I alluded to earlier, we can start with a simple version of this, but you come across complications quite quickly. So quite quickly you start thinking, do I really want every unique token that I break down by documents or queries? Do I really want them all to be considered unique? Or should some of them kind of be rolled together and effectively considered to be the same word? A really simple example of this is casing with words. Now to a human, the word cafes, big C, and cafes, little c, are the same. But computers are vernacular, and so we're going to have to tell computers ignore the casing of the words. Essentially, we just say lowercase. This particular action is called normalizing casing. But the more general action we're doing is called normalizing terms. Normalizing casing is just a type of normalizing terms. Another example is accented characters, or removing diacritics, if we're being fancy, where diacritics are little shapes like the accent, the squiggle, the dart, or the darts. And like to a human, the word cafe, accent, is probably the same as the word cafe, no accents. So if we want computers to think they're the same, get rid of the accents. Now the next slide has something a little bit more complex, a concept called word stemming. The idea is to reduce words down to like their root essence, or the stem of the word. And we can do this to normalise plural versions of nouns, because again, if I'm searching for cafes and a document has the word cafe, that's going to do it. I don't care if it's single or really. And we can use it to normalise verbs. So pushing could be matched to push, or pushed could be matched to push, and pushed and pushing could be matched to each other. For the purpose of searching, we're just considering it the same way. Now, it can even be extended with rules to cover less regular verb formations or noun formations. So running and ran, people, person, cactus, cacti. This is normally, probably most commonly handled by having a bunch of really specific rules for all these different types of irregularities. And these rules are going to vary depending on the written language. So if you've got English language, the verb formations, the noun formations are different than you have. So all these rules are going to be specific to one written language. Now another technique is to add support for bunches of words that kind of mean the same thing. Delicious, tasty, starving, hungry, and then they're hungry on this slide. One word is meant just the canonical representation of each concept. And again, this isn't something you can just have a set of rules. It's going to be like a big lookup table, and this again is going to be particular to one language. It's not going to work in French. Next topic. Abbreviations could feasibly be handled like synonyms, but while synonyms only rely upon the written language, abbreviations are also dependent upon context in which they're used. So you can't just say NS always means microsecond, or MS always means milliseconds. It depends. You don't really know unless you can somehow take into account the surrounding words, which is most appropriate. And if lexical is all about considering words in isolation, that's not going to be its forte. Right, I promise we're nearly done with this lexical stuff. And it will make sense why I've got into it so deep. When we talk about normalization, we're defining rules that apply to tokens when they're generated from source documents during indexing and from your queries. Now, a similar process may be applied only to tokens that come from queries. So, for example, to try to improve matches when there's a typo, you might generate variations on a word by performing like little simple character transformations, like considering any variations that come up that exist in the index, just be like they were probably maybe the same word. Maybe we take that TF-IDF score and reduce it, and we've had to mess about with words a little bit to make it fit. But you know, it should help us be more forgiving of general, real use cases of people who aren't always. Now, if you use Elasticsearch, it has something built in to do this. It has an option to enable fuzziness auto, and that will allow a number of simple transformations based on the word's length. If you've got a word that's only 1 or 2 characters, no transformations. If it's 3, 4, or 5, 1 character translation. 6 or more, 2 character transformations. So, for example, if you mistype in your search curves and you drop the E, because you forgot how to spell curves, I don't, it would match it. That's a 6-letter word. Your typo, though, is only a 5-letter word without the E. So that means it will allow 1 transformation. It's like, ooh, if we shoved an E in here, it would match up it. Yes, we do. Okay. So it's convenient to have the computer sort of allow for these little minor mistakes rather than punishing you and go, 0 results. Now, similarly, you might have people who disagree whether the British spelling colour is correct, whether the American spelling colour is correct. And depending on whether that's in the document versus the query, or query versus the document, this type of forgiveness will make everyone's life easier. It doesn't always improve things. If you search for Dan, you kind of expect it to match documents, which only have the word Dan in. But with this type of forgiveness, it might say, well, what if there's words, documents with the word can in? It's going to bring that back. And it's all well and good to say that we'll give a lower match score to these imprecise matches, but it still brings about this confusion. Why does this result even come back? In fact, I worked with someone on my team last year called Karina. We were experimenting with this Elasticsearch option, and she was doing searches with her own name, and couldn't understand why search results were coming back until she realised how close Karina and China are. Karina is 6 letters long, so it's allowed 2 transformations. If you drop the first A and replace the first A, let's get it right. Right on the screen as well, isn't it? Change the first A for an H, that's 1 transformation. Remove the R. Karina becomes China, and she now realises by searching her name, was bringing back all these documents from China. It gets even more confusing to work out why particular results are being returned if we're being forgiving about possible typos. It gets even more confusing if multiple normalisation rules may be applied. So, for example, if someone searched for unit tests 2 words, they might not imagine that it would match a sentence such as, I included a text file for the primary units. But what happens is, word stemming reduces the word tests to the singular test, and word stemming reduces the word units to the singular unit. And then the typo forgiveness will allow a matching test against text, because that's just 1 character transformation. And so that search unit test does match this sentence. People are like, what is going on in most results? Now that example included several words getting manipulated, but it can occur even with single word queries. So when we search for a single word using a lexical approach, like if we search for the word cat, we don't really know if the person searching means cat as an animal or means cat as an abbreviation of cattle. And in an ideal world, our search logic would somehow go beyond treating text as just sets of isolated words, somehow have some kind of understanding of the context in which they appear. But since things are already getting quite complicated, this simple lexical approach, as we add more and more rules, maybe it's time to start from scratch with something new. What we're going to talk about is taking a machine learning approach, lots of text from the internet, and using a trade that semantic textual similarity embedding model, and using that for searching. The function of a semantic textual similarity embedding model is to take text as input and calculate a vector that represents that text, which may, depending on your background, lead to the question, what is a vector? In C#, most commonly a float array. So an array floats up with numbers stored as 32-bit, 4-byte data structures. In maths, a vector can be like a pointed space. So in 2 dimensions, it's a point on a graph. In 3 dimensions, it would be like a point in a cube. In 4, 5, 6 higher dimensions, it's a similar concept. It's just how the human brains are picturing anything all. Now, a given model always generates a vector of the same length, and it's actually commonly hundreds of dimensions. But it can be beneficial for the purposes of envisaging what I'm talking about, so pretending there's only 2 dimensions. The crucial property of these vectors is the vectors that these models generate. 2 vectors will be near each other if the text that generated that vector is similar in semantic meaning. So each vector here, specific points on the graph, to reinforce something I kind of skipped over a bit earlier, the output of an embedding model is an embedding vector. Now you may hear embedded vectors referred to as embeddings or just as vectors, but it's the same thing every time. So we have the vectors represented as points on the graph, so it's easy to visualize how similar they would be. It's how physically close that points are. So now that we know kind of what vectors are and understand that embedding models are magic boxes which see text and calculate embeddings and vectors that represent the text, leads to the question of what are embedding models and how do we create them? It's complicated and it's expensive. It takes a lot of compute, it takes a lot of genius. Thankfully, there are some friendly research labs who do this hard work and actually make these models work. So we're unlikely, in reality, to be in the business of building embedding models ourselves. However, if you want a tiny insight into how it works, you can start with something similar. Word to vec is a technique that was described in a 2013 paper written by some people at Google. It consumes sentences of training data and breaks them into tokens and feeds these sets of lists of tokens into some machine learning algorithm data. In order to produce a trained model that can take individual words and return a calculated vector for any individual word you give them. Words that are similar to each other will be vectors that are close to each other. Now, as you can probably tell by my handwriting famous, this is not an area of expertise. Some years ago, I was curious and found someone online describing a C# implementation. I resurrected in case you want to try it for yourself. I'm going to include a link at the end of this to the slides if you're desperate to go and try it out. There's a link to the original Google paper. It's a really good explanation because that's like an academic paper. That's it. I read it, I get scared, and I close it. So the explanation is really good. Unfortunately, the original page where I found this code doesn't exist anymore, but through the Wayback Machine, it does. So I found the code, and I've also put it up on the GitHub repo. Hopefully not breaking any license or anything like that. And you can run it, you can get this, you can run it, you get a text file. Once you've trained a model, you enter the individual words this console, and it will calculate a vector. And then it looks at all the vectors from words that it encounters during training. Okay, bear with me please. I'd like to blame Josh for this, but I he's him. Josh, am I still in the meeting?
Don't worry about the meeting, we've got the presentation, so don't need to worry about the screen share.
Okay. Sure how many slides there are. Okay. Go. Train the model. Train the model. Train it. Actually, an individual word is this console, and it calculates a vector for that word. And then it looks at all the vectors, the words it encounters while it's training, and it compares them to the vector of the word that you vectored. And then it gets the top 10 closest vectors, and those vectors should be associated with the words which are closest to the word that you vectored. So I tried running the C# code with 1 million sentences of English language news content that I downloaded from this public data set, and then tried searching for a few words to test it. And it's kind of crazy that it can do this by just treating words as numbers. It has no concept of language. If you trained a model using 1 million sentences of French, it would work well with French words instead of English words. And the entire code is only a few hundred lines long. Well, let's go back a little bit. If I said we don't build our own embedding models, where do we get these public models from, these friendly research lab publishers? So a great place to start is a site called Hugging Face. It's described as a collaboration platform, open source models and data sets. Great place to start. You can download these models and you can use them. So let's just recap quickly before I push on. With lexical search, we index documents by tokenizing those documents, building a lookup tree, and to query, we tokenize the query text and search for each individual token in the index. With a semantic search, we index by using an embedding model to calculate vectors for every document. And to query, we use that embedding model to calculate vector for the query and try to find the document vectors which are closest to the query vector. For lexical search, we construct the index only by using the documents that we have that we want to search in. And then we have to concoct this bunch of rules to handle things like plurality and typos and stuff like that. Semantic search, meanwhile, uses an embedding model. And embedding models train on huge quantities of text, and they actually learn how words relate to each other, kind of like how we saw with word today before. And this means that it will recognise that in phrases like crazy cat man and crazy cat guy, that the words man and guy in those contexts are very, very similar concepts. And this level of comprehension means that it will recognise variations of spelling, whether it's American colour and British colour, or whether it's common spelling mistakes, as being the same concept. In other words, as long as the embedding models are trained on enough data, there won't be any need for this extra logic for handling the special cases. Part of the reason that dedicated software exists for full text indexing, like Elasticsearch, is that storing text indexes, such that to search, critical data, to add or remove, benefits from software and data structures designed to do so. Now you could try to build it using table format data if you wanted, but it wouldn't be very efficient. Similarly, vector databases exist for storing and searching vectors, and they exist so they can do this job specifically, efficiently, effectively. So for example, if you want to search across tens of millions of documents, you have to vectorize your query, and then you compare that query vector to the tens of millions of document vectors. And if each vector has hundreds of dimensions, you very quickly get to a huge number of computations, comparisons, and you quickly get into a situation where search is quite expensive. Well, vector databases use kind of tricks. They use something called an approximate nearest neighbour, or ANN, index to avoid this brute force approach. It essentially groups vectors by vicinity. So when you do a search, it just has to check vectors in a bunch of groups instead of all tens of millions potentially of vectors. And you wouldn't get optimizations like this if you didn't use software that was tailored to deal with vectors. So there's various providers of vector databases, such as Weavegate, Pinecone, Elasticsearch, Postgres. Now, I said earlier that Elasticsearch is a text index database, but some years ago they started extending it to support efficient storage and searching vectors. Postgres is traditionally a relational database, so all bit stages are tables. But it has an extension for storing and searching vectors in this efficient way. So, say you've selected a vector database to use, then you're going to have to deal with something I've breezed over so far, how to choose an embedding model. Because different embedding models have different characteristics, and any given embedding model is going to generate vectors of the same length, regardless of the text given to it. And there's a very general rule: the larger the vector, i.e. the more dimensions it has, the better at differentiating text it's going to be. So it's either more accurate, the smaller text, or better able to handle big pieces of text. But more dimensions means more storage for the vector database, more compute costs in calculating vectors, more compute costs and time in searching within those vectors. The first four things on this slide: indexing costs, storage costs, search speed, accuracy. You can probably work them out without worrying too much about the source of text data that you're looking at. So you start with a commonly used model, experiment a bit. If indexing or search is too slow, you could have your model in your vector database, like hosted somewhere with more resources, just crank up the size of your service. Or you could try that model, try a different model, calculate vectors with fewer dimensions. But the last one may require some analysis of your data. For example, people think about questions and answers when they think about Stack Overflow, which is pretty fair, since the main website is just questions and answers. It's short form content. But within this Stack Overflow for Teams product, make a little money, We support articles, which is a long form type of content. And to index them, sometimes they're too big for the embedding model to do a good job of. And you may have to split them up and index it as multiple vectors for one big document. This is known as chunking. This is document's too big, it's slicing. But there's so many ways that you could do this. You could split an article into just individual sentences to read that. Well, A, you would end up with a lot of vectors where you thought you would just have one. B, you don't get a lot of context in any individual sentence, and so it's not going to be a very effective search. So you're probably going to want to join bunches of sentences together into each chunk. And you could just do this by saying, let's cram as many sentences into each chunk as we can fit before we go on to the next one. Or you might go a bit crazy, it's clever, but you might look at it and be like, I'm going to use more machine learning and try to guess when a sentence is beginning a new topic. And that's a good point at which to break and make a new chunk. What I'm getting at is there's a lot of ways, there's a lot of things you can do. So that's all I want to say about it. We're going to move on. If I go deep into everything, we will be here past the So let's move on to the next thing. How close should vectors be to be considered similar? Because this again is something I've sort of breezed over as if it's going to be dead easy. So when we have an index of vectorized content, I'm moving forward search by vectorizing the query text, getting the documents whose vectors are closest. How close is close enough to be good? Like, if we get the top 10 closest results, are they always going to be good? Well, rather than just be theoretical, something a little bit practical. This is supposed to be a .NET talk. So there is mention of C#. So I've knocked up some code you can get from GitHub that uses data from a Stack Exchange site called Workplace. For anyone that doesn't know, Stack Overflow isn't just the name of the Stack Overflow site, this Teams thing I keep banging on about. It also has all the interest sites. So there's one about coffee, there's one about pets, there's one about auto mechanics. I've chosen the Workplace site because it's big enough to be interesting. It's got like 145,000 questions and answers. It's not so big it would take forever to index if you wanted to experiment, try this model, try this, and try this. And importantly, it talks about subjects I know enough about that I can judge whether the search is good. So this example, that you might have to visit my slides after a download, playing love, is uses an embedding model from a plugin fix called E5 small v2, and it uses Postgres as vector database, using the PG vector extension. Now, if you want to run it yourself, you need to download a data dump from this Workplace site, but that's really easy. You just register an account, go to settings, download data dump, something like that. The GitHub repo has all the instructions you need. And once you've got the data dump in your project running, it will execute some searches that are defined in code, one of which is, what is the best office chair? Now this is the sort of thing that Workplace is great for. Questions about working in the office, telling your boss you want a promotion, working out how to deal with co-workers with interesting habits. The distance value is a measurement of how close the query is between the document vector and the query vector. Smaller distance, closer. Closer, more relevant. And these results look good. You probably can't read them from there, so you'll have to say my word for it, but they're decent. Now search, I would not expect Workplace site to be amazing for is, how can I train my habit to swear for comedic effect? It's got results though. It's got results. It's got the top 3 results. However, it's clear that these are just the top 3. The best of a really bad bunch. Like, none of these even mention habits. So what's even more confusing? Depending on how much attention you were paying on the last slide, these distances are actually smaller than the distances on the last slide. So the distances here of these rubbish answers are even smaller than the distances of good answers. So I've kind of thrown out a trick question. How close is close enough? There is no simple threshold below which it's a good answer and above which it's a terrible answer. So I'm going to introduce another concept called a re-rank. A re-rank is a different kind of machine learning model that you use after you perform a search. Not after the user performs a search. The user performs a search, your clever search does a bit, and then does a bit. The idea is that you cast like this wide net using quite relatively cheap mechanism. And then you run a more expensive, but more accurate second pass. The vector search is like our cheap part. particularly if it's using one of these clever approximate nearest neighbour algorithms, it's super speedy. Because a rewriter can deal with hundreds of documents, but it can't deal with tens of millions of documents. Vector search can do that, you can do it quick. So again, the vector search has to widen out, get more results than we want, and then try to improve that set of results using the rewriter model. The rewriter specialises in giving a reliable score that represents relevance. The score is all that it gives. You give it a document and you give it a query and it tells you how relevant one is to the other. It doesn't like it embedding vectors, so you couldn't use that for a vector search. And another benefit to them is that bigger and more expensive, when you're doing on such a smaller amount of results, some of them can take the full document, so all that chunking complication gets discarded, gets thrown away. So say that you wanted 100 results, you might first try 200 from vector search, it's called overfetching using a cheap mechanism. Then use a rewrite to tweak their orders and take the top 100. Or even better, the rewrite scoring may allow us to identify results that are just rubbish and get rid of them entirely, which would fix the square pattern problem. It's not going to return you answers about how to teach your parrot how to swear because they don't exist, but will at least tell you, I can't answer that, instead of giving you answers which is just crap. So, fantastic, semantic search, silver bullet. Well, it tends to give good results in natural language queries, with the caveat of putting in a rewrite afterwards, so that we know how close is close enough. And when the documents that you have are not completely foreign, when compared to the text that was used to train the embedding model. So if your embedding model is trained in English language, and you try to use it for search in French, you're probably not going to do great. Or if you've got lots of specialist jargon and acronyms, things like that in your content, it may also struggle with a pure semantic approach. Now, if someone's searching for very precise terms, or searching in a keyword style, rather than typing in a natural language, so if you're specifically searching for one keyword, lexical might actually do a better job than semantic. So maybe we don't want to discard lexical entirely. Maybe we want a hybrid search. This is where we perform semantic search, and we perform lexical search, mash the results together. Now the relevancy scores from these aren't comparable, because semantic is vector distance, and the other one is some TF-IDF, whatever comparison. You can't say which, you can't compare one to the other. So you need a way to combine these results, which doesn't try to use their scores. Commonly used ones called reciprocal rank fusion, RRF, which sounds really fancy, but you can look it up in a simple calculation. You combine these two sets of results. These algorithms, these combining algorithms, they allow you to say how much weight do you want to give to one or the other. Now you can't just always say give them both 50-50 and just move on with your life. Or you can say, I'm going to use something called search query analysis, which decides what weight to use based on what kind of query you do. Now if it's a single keyword search, that's probably really reflexible. So let's do like 90% lexical, 10% something. But if it's a longer text, that looks like a natural language question, we're going to lean more heavily to semantic. 90% semantic, 10% lexical. Could be anywhere in between different points of dimensions. It's another topic that I'm not going to go any further into, keep things moving. So let's move to like a visual reminder where we are in the search process. Looks like yes. We can see the query coming in. We can see it being matched against potentially millions of documents. This is casting a wide net in the search using semantic and keyword searching. And we take those results and we improve them further using the re-ranking. I said earlier that an advantage of using the embedding model to train on lots of text is we shouldn't have to worry about loads of edge cases like we did with lexical. But it does also seem like we're quite quickly gathering other types of complications as we get further into it. So can we now finally be happy with what we've got? I think you probably pick up on that. I think you might know what this is going to be. No. There's still a lot of other techniques that you might have to explore depending on these. Something called quantization is great if you have to deal with huge data sets and you're finding that search is moving faster or you need to reduce storage costs. Quantization is essentially saying instead of storing things as 32-bit float arrays, let's use something called a compressed vector, so we use a smaller data type. Could be a scalar, could be an integer, 8-bit. Now it will reduce the accuracy, but surprisingly not quite as much as you might think, and increases search speed significantly. Some people are even experimenting with 1-bit vectors, which which is where you shrink it down 32 times. Much faster. But again, not quite as accurate. We've got this rewriting. Who cares? We can be doing tens of millions of documents super fast, getting rough results, 400, shove them into a re-ranker, get 100 really good ones. Okay, so it's smart, it's fantastic. So we can use the re-ranker to filter out rubbish results. But it's worth noting that embedding models, some of them work better with quantization than others. And so you're going to have to test your data, which is an unfortunate thing that keeps cropping up. That you can't just say, this is the best practice. Multi-vector indexing is good for giving weight to certain fields, like the title. You might index the title separately from the body. So it improves the results in case where you kind of know the name of something, but not the content. Query rewriting is something that can help with personalization, which is definitely out of scope for this sort of, I'm just going to very briefly touch on. It's where you take something that you know about your users. So maybe you have something buckets and categorization for user. Maybe this person generally looks at Python questions, and maybe they're quite a beginner. You take the query that they've entered, which might be like, how do I add an item to a list? And you prepend, as a Python beginner, how do I add an item to a list? So you use something we know about the user to try and improve their experience. Fine-tuning model, embedding model, fine-tuning. Not something I'm going to get into now, but it's an interesting thing to raise. The gist is, you take one of these expensive to build, off-the-shelf embedding models, and then you like finesse it by showing it a bit more data. Like you might have private documents that you want to index, which talk about this exciting new project Phoenix, and you want the model to understand that the context in which it's used, Phoenix is not like a mythical bird or a race in America. And this addresses the caveats that I mentioned earlier, where I said that embedding models may struggle if you have lots of jargon or acronyms, because you're essentially extending the embedding model so it does understand the terms like that you use in your documents. Now, any or all techniques here may make your search more accurate, make it faster, or you may unintentionally make it worse. And what's going to be really key is being able to measure the effects, the changes that you make. And how do we know if we make things better or worse? We can't just record what results are coming back from searches. It's how do we know if those results are good? Say you do have access to your users' data, you can see all the searches they've done, and all the results they've got. How are you supposed to know if those are good results? And even if you did, that does not scale very well. I don't want to improve my system by having to look at everyone's success search results. What we really need to know is, what does the user do next? Like, do they click on a search result, and then stick on that page for a while, and then leave? They're probably quite happy. Probably found the answer they wanted, read it, enjoyed it, went off and implemented it. Did they get the results page, and then just leave immediately infuriated? They're probably not very happy. Did they do what a lot of awkward people, by awkward people, I just developers do? Which is what I did, which is get a search results page, you go, middle click, open them all separate tabs, read the first one, don't like it, close it, read the second one, stay on it for a while, cool, leave those tabs open, obviously, forever. Go and implement it. They're probably also quite happy, just not as clearly, obviously happy as the others. We need to see what the user behaviour is to work out if we make things better or worse. Because make things even harder. Changes that we do might make it better for some users at the cost of making it worse for other users. Like some people are really good at their keyword formation, and then we're trying to lean into this natural language thing at the cost of that. We might make them furious, while we make other people's lives better. Now, at Stack, where we're implementing this form of search, we actually don't have access to our customers' data. I can't see the queries that they're doing. I can't see the titles of postings that they matches. So we work on representation lines. So we might store a query categorization. Does it seem to be a single keyword? That's one category. Does it look like two keywords? Does it look like a long natural language query? So I have like a category query. And then we like trace the subsequent user actions, but not any of the data about the title they saw or the text they saw. And this is always going to be a slow process because you've got to deploy the code, you've got to observe the user behavior, you've got to hope you haven't made anything like ruinously worse, such that they get in touch with their support people and go, I hate you, you're not going back. So you might want to get faster and safer feedback on ideas, like simulating user happiness. Because if it was possible to run tests about users, you could run lots and lots of variations much more quickly and without risk of ruining it all day. One way might use it with your own company data as opposed to developing this product. Or you might use it with data that you can get from some of our Stack Overflow interest sites. You use an LLM, which is a large language model, which is the sort of thing that ChatGPT is built on. And you get some of these articles and questions and answers, and you say to the LLM, generate questions for which this is the right answer. And then, when you think you've got a beautiful, wonderful search system where indexing that data, you run these questions through it, and the post, like content from which those answers were, those questions were generated, should be in the top results. Otherwise, things are presumably not wrong. Something that requires quite a lot of experimentation is a research topic. Another approach is to use an LLM to judge. This has the phrase LLM as judge. This is using an LLM that's similar to a research, where we would say, I think this is good relevant content or not. And then you might take searches that people have run. Again, we can't do this with our custom data, but we might do it with like our internal data or our public data. Run actual queries that people have done, such real searches. And then for the results that we get back, ask an LLM to judge how good are these results. And that can be a way to experiment, and to iterate, and try. The real test is users, but users is expensive. Now, with all of this exciting research taking place, all the great results that bring about quickly, it's easy to get carried away and think you can just plug something in straight away read reports. So I probably, if you sat through this, you don't think that that's easy. But maybe your CTO, who heard from a man on the golf course that his nephew has done some artificial intelligence and it's really easy, might think you can just plug it in and read the reports. Well, there's so many things that you can tweak and change and fiddle with that while you can get quite quickly to this is better than what we had most of the time, but it's sometimes weird and it's sometimes utterly wrong. To get from there to this is genuinely really good is going to take quite investment. And getting it right really requires this user behavior tracking that often isn't available. So it could be that it's your software, it could be development work required to do that. And then you benefit from data like this because it's horrifying trying to turn those events into is that user happy. Speaking of user behavior, I realise I keep mentioning tracking user behavior actions quite a lot, which kind of sounds a lot. There's enough governance, there's enough companies tracking my every move. We don't need to answer the problem. But really, we can just be tracking actions like performed a 7-word query, looks like natural language. Clicked on answer 1, 2, 3, stayed for a second, went back to the results, clicked on answer 4, 5, 6, stayed for 10 seconds, left side. It can all be totally anonymised and aggregated. You don't even have to record what user that was, just that it was the same user who went through. No privacy. Now we're getting towards the end of this talk. One more thing to reinforce, which is that with all these hurdles and complexities, what hopefully makes it worthwhile is search is always going to be important for exposing content, making your website or your application useful. Because unless you can rely on a public search engine like Google to find your content, which is what public Stack Overflow is basically been surviving on, and technologies like I talked about today are going to be increasingly useful as users are so used to Google logic. And it's worth bearing in mind that it's not just like type question, get results, that is powered by search. Anywhere that you see some like recommendations or suggestions, powered by search. We're starting to add this facility to our Stack Overflow team product called generated question answering, which is a form of search, and because we're getting these amazing results, it looks like someone has asked the question, it's not just searching for keywords. We will take the content of those results, shove them into another LLM, and try to generate an answer for the question specifically that you asked. So often, they won't even have to click into the search results. The search results page will tell you the answer, which is going to make user behavior tracking even more valuable. That's another problem. Make everyone else delighted. We're also going to hook this generated answer. Generated question answering. We're going to hook that into Slack, MS Teams, another product called Teams. We've got Teams, they've got Teams, names as well. To answer questions, so you can be like in Slack, go, hey, private Stack, tell me the answers to this, and it will tell you right in Slack without having to move, because I believe that people don't like leaving Slack or the idea. Speaking of which, I've got an extension for VS Code, which is the same sort of thing. Wow, I think it's an exciting time. I may be biased, because I realised when I was preparing this, I have spent well more than a decade, basically, on search or on things right next to search. So you might not all agree, we might agree, in which case, feel free to hit me with questions. It's the first time I've like given it to people. I'm like, it's mine.
Do you feed the generated responses back into your Stack Overflow data set?
Good question. I like it. Yeah, we're thinking of experimenting with this. Like, are you happy with this as an answer? And does it seem like there isn't an answer that encapsulates that already? Now, what we don't want to do is do any of that like in a totally automated fashion. We want to keep human in the chain, because otherwise we perpetuate this problem, which I'm sure you're alluding to, which is the dilution of good content through just being drowned out by computer-generated content. Yeah, that's a good question.
So in the semantic search that you mentioned, we were doing the chunking before feeding into the embedding model into the LLMs. So how does that chunking help? Is there any upper bound to what is the length of the chunking? Like it's some 1,000 bytes or the organization.
So, different embedding on, I realise I should be repeating these questions for the benefit of YouTube. Question was, how do we decide how to chunk? So one thing to bear in mind is, each embedding model will have a different limit on how much content it can consume. It can generate effectively. So if you had an embedding model that could take large amounts of data, then you would have fewer chunks. I want fewer chunks because each chunk will contain more context and it's more likely to match the query. But it really is a massive subject, because even if you try to use another model to say which sentences contextually seem like they live together and can we fit them in, you might still want to kind of have overlapping chunks, because quite often the context isn't like the black and white in a split. We're still in the phases where we're doing very rudimentary breaking down content. And although we have articles now in our team's product, they tend to be less than 10% of the total number of posts, where a post is an article or a question or an answer. So with most of our content is question and answer, which we probably just initially. So sorry, it's not a very informative answer.
So does that depend on the amount of query, like the chunking? Does it depend on like if the question is of let's say 10 tokens, so the chunking will be like 10 or multiple of 10?
So quite often, I think the embedding model we use can support up to 512 tokens, where confusingly, token is a different concept than it was in lexical. Lexical is a whole word, and semantic tends to be like a fraction of a word. Like on average, rules of like 4 characters. So 512 of those is 2,000 characters. It's not a huge amount of content, but it's often enough for question and answer. And like a really quite rubbish way of doing it, especially for short form content, is just a call. And just hope there's enough context to start. That's it. That really good search results. But yeah, it's a broad subject. There's a lot of things to try. Josh,
Did you know what you were getting into when you stepped into Stack Overflow? Did you know the search area, and what was the experience you had in search before you joined the team?
good question. When I joined, this search project was not like active. It's something that we knew was not really good enough, but it wasn't until last year's sort of explosion of seeming like these AI technologies were affordable enough and mainstream enough that it opened the door to these sorts of experiments and improvements. So I'd been at Stack for, 18 months before that. But 2 jobs before Stack, I worked for a startup called Curiosity, who small, based in Germany, worked remotely, it was great. And they were kind of ahead of the curve. They were using these interesting AI models and technologies and things that I just did not know anything about as I worked there. It was my head into a spin. But I came away from there thinking I hadn't absorbed that much of it until this subject matter came up and I realised, oh, that's that. Oh, that's that. Well, that's that. So curiosity like prepared me for this AI, semantic, very modern type of search really, really well. But before that, I worked for this tourism company where there's lots and lots of. It was basically how you find stuff. So I've been interested in search. It's the sort of work that kind of invigorates me because it combines two things that I'm really interested in, which is like scaling and user happiness. It's like I like things where you know someone's life, if not better, a bit less miserable because so many ways. And this scaling is just there's so many facets to investigate. It's interesting. So it's always been kind of an interest. So this has been kind of a dream opportunity for us.
So you have mentioned something about hybrid search.
Yeah.
Okay. And you mix two kind of search there, and you maybe assign some weights to each of the search, I guess. How do you determine the weights because it can change over the time as well?
It can, absolutely. And we are at the moment just doing a fixed weighting. It's one of the things on our list to experiment with. I'll be really honest, I hope this isn't too honest. We're still working on making sure that we've got enough user behavior, action, event tracking, and enough data pipeline, data analyst magic, that we get to a position where those things, which they're not in the weeds, but they're also not like big wins, where we can actually definitively measure are these sending things in the right direction. So we're kind of crossing off a lot of the broad strokes with this. But before we get too deep into chunking, before we get too deep into the query analysis and the weighting for the we're not quite there yet. So we're just sticking with 75 semantic, 25 lexical.
That's magic numbers.
Yeah. Thank you. I need reassurance.
This is small way.
I worry that you two are coming in a lot more than
So in this one, there's a technique called RAG, like retrieval augmented generation. Are you using the same technique in the semantic search?
Sorry, say that. Is the re-ranker?
So in the semantic search, so there's a technique called RAG, retrieval augmented generation.
Yes.
So are you using the same technique in here?
We're using that, not in search, we're using RAG, retrieval augmented generation. That's how that facet of generated question answering, that uses RAG. It's actually a different team that uses that. Well, of course, it's built on top of search. That's kind of what I'm trying to get at, that we're like the crooks of everything. I'm taking credit for everything. Everybody will build it. Both good? Any more for any more, or is it beer time?
Thanks, Dan.
Nice, thank you very much.
So last thing for me, resharpen giveaway. So we've got the license, great colours. Oh. Congratulations.
Hello.
Congratulations.
Thank you very much.
And I think our first live session, thanks for being out here, Dan, for that one. I think it's gone really good. We lost the connection to the shared screen like 10 minutes in. So yeah, Chris has been frantically going through the presentation one at a time, so hopefully he's kept it all in for us. But yeah, stick around. We're going to just tidy up the boxes and stuff, but there's loads of drinks out, some pizza there, help yourselves. We've got the room still in about half an hour or so, so if you want to stick around, we need to shoot off for transport. But thank you all for coming. We want to have a community like this, and we didn't get people out, and you know, we've auditioned today, we've got a really good turnout, so thank you all for coming, and we'll hope to see you again next month. Thank you.